Today, I would like to introduce the final project for course EE512. The name of my project is 3D Human Pose Estimation with GCNs and Bayesian Optimization. My name is Oliver Swan. The motivation of this project is, in human-robot interaction, 3D human pose is essential to understanding user status and intention. However, current work only focuses on 2D human pose estimation with RGB image, which is not sufficient enough to estimate, for example, human orientation on grounded plane. We also observe that human body follows some geometric constraints, which gives us the intuition to reconstruct the third dimension from a 2D estimation. As an overview, I separate this work into 3 stages. In the first stage, the 2D key point detection and normalization using pose detection gives us the 2D key points with the RGB image. In the second stage, we use GCN regression on normalized 2D joints to predict the 3D joints. In the third stage, we use Bayesian optimization to search over constraint weights. On the right, we can see the human 3.6 million rest pose, which consists of 17 joints. In the first stage, we use 2D key point detection and pre-processing, which uses a HRNet-based pose detector fine-tuned on human 3.6 million, normalizing the input to positive -1, centered at image midpoints. We also center the 3D ground truth as the pelvis root. And this ensures the scale invariance and zero mean inputs. In the second stage, we applied the GCN regression model, which uses MLP for the input encoder, encoding the 2D joints to a 64-dimension embeddings, and then 5 graph convolutional blocks with ReLU plus Bayesian normalization, and the adjacency matrix is defined as below. The output layer predicts the 3D offsets plus the root. The anatomical constraints introduces some inductive biases to the model. It totally consists of 12 differentiable losses, including hip straightness and bone length ratios, and is activated after epoch 20, linearly ramping up to epoch 40, which gives us the total loss defined as the MSC loss plus the weighted ramped loss. And this encourages realistic articulation and anatomical plausibility. The 12 hyperparameters are demonstrated as on the graph, and we are using Bayesian optimization to search over each of their ranges, ranging from hip straightness, shoulder angle, neck thoracic spine, etc. And after the search, we have discovered that the hip straightness, which states that the left hip, the pelvis, and the right hip tends to stay on the same straight line. And this weight ranks on the first. We also have this neck spine straightness, which states that the neck, spine, and the head tend to be on a straight line. And here's the result. On the left, it's a 2D human pose detection yielded from pose. And on the right, the blue points are the ground truth points, and the red ones are our prediction. You can see that they are already pretty close, given that we only have 12-dimensional data, and we want to infer the 3-dimensional data. As a conclusion and future work, this work uses GCN plus anatomical constraints to bridge data-driven and domain knowledge, and uses Bayesian tuning to automate loss weighting. The strong bias helps improve 3D recovery by introducing inductive bias. In the future, we will integrate RGBD, where D stands for depth, or video for higher precision 3D pose estimation. Thanks for listening.